Okay. So, and if you use this, then you can rewrite your equation of state as P times V equal to little n times R times T, where little n is nothing but the number of moles in your system. So it's the number of atoms or molecules divided by the Avogadro number. Okay? Great. Now, of course, I told you that this equation of state is applicable only to gases at extremely low densities, right? If you want to consider the equation of state for a gas at finite density, there is a phenomenological equation of state, which is due to van der Waals. That essentially tells you how to generalize the equation of state for the ideal gas to account for two basic effects of interaction. So van der Waals thought about molecules essentially as billiard balls, in a sense. So if you have two molecules, they cannot, compenetrate each other, first effect. And the point is that if they cannot go through each other, if you have one molecule that is moving around, it doesn't see the whole volume of your system, but it sees only the volume minus the volume of all the other molecules, right? So in order to account for this, what you do is you take the equation of state for the ideal gas and you substitute to the volume V minus B times N, where B is, in a sense, the excluded volume of each molecule, right? I mean, the volume you cannot see and you cannot go through when you have a molecule that is moving around due to the other molecules that are sitting there. And also you have to account for another effect of interaction, which is the effect of long-range tails of the interaction. I don't know if you've ever seen a van der Waals potential, which is another one of these phenomenological potentials that are used by so it's looking like this. It has an excluded volume, so it's essentially infinite walls. And then it has some long-range tails that look like this. All right? So now you want to account for this long-range part of the interaction, and this long-range part of the interaction will essentially change the pressure in your system. It can be accounted for by renormalizing the pressure in your system. The reason is that essentially, if you think about it, when you have interaction, so pressure is due to the agitation of molecules, right? When you have interactions, these molecules are in a sense correlated to each other, so you don't have the same pressure that you used to have without the presence of other molecules. And the way to phenomenologically account for this is to rewrite the pressure as P plus A, which is one of these constants that come from van der Waals potential, times N divided by V squared, the density squared. Okay? It's not easy at the moment to understand why the density is squared. It's essentially due to the fact that you have binary interactions, but one promise that I can make now is that towards the end of middle of November, we will derive this equation of state that I'm going to write now, the van der Waals equation, using something that is known as a cluster expansion in statistical mechanics. So you will see where this equation comes from microscopic from the microscopic theory. At the moment, we are just writing it phenomenologically. So phenomenologically, the van der Waals equation of state is equal to n times r times t. You see, it's the same equation of state as the ideal gas equation with these two ingredients that change the entropy, the pressure and the volume.
Sorry, is all of this procedure valid for lower dimensions like 1 or 2-dimensional ideal gas, or does the situation change that?
Why should it be different in 1 and 2 dimensions?
The form essentially...
One dimension, I'm not sure, because in 1 dimension, you see, 1 dimension might be tricky. So 2 dimensions is not a big deal, because in 2 dimensions you can... But in 1 dimension, if you have an ideal gas, in 1 dimension you have an excluded volume, you see that if I have 2 balls here and 1 ball there, it's not that just it cannot enter here. It cannot go through, right? So it's a very subtle situation in 1 dimension. But in 2 dimensions, it's not a big deal, because you have this guy and this other guy. Well, this guy cannot enter this volume, but can go around it. So 1 dimension might be tricky. 2 dimensions should
more or less should be the same in 2 dimensions.
I think in 2 dimensions it should be the same. I mean, it's going to be an excluded area, not an excluded volume, but it should be more or less the same philosophically. In 1 dimension it might be subtle, so it could be complicated. Finally, let me make another example of an equation of state, which is the Curie equation. Which is an equation that describes magnets, not gases. And it's something like magnetization divided by volume equal to constant times magnetic field divided by temperature. Okay? So all of this we will see later on in statistical mechanics. All right, so up to now we have been discussing general principles of life, general description of essentially experimental facts. Okay, equation of state is an experimental fact. The fact that you have to modify it by the van der Waals equation is another experimental fact, and so on and so forth. So now let us set down the rules of thermodynamics, which are the various principles of thermodynamics. Now, when you write down the principles of thermodynamics, it sounds as if these are just trivialities, okay? And the reason they are trivialities is that you were born approximately 200 years after these principles were invented, okay? But they were not trivial when they were invented. It took a long time to understand the concepts behind the principles of thermodynamics. Now, there is one principle that is typically never stated in books that is trivial, is indeed trivial. That is the Zeroth Law of Thermodynamics. The Zeroth Law of Thermodynamics, so if you open a random book, the probability to find the Zeroth Law of Thermodynamics is, I don't know, 1%. That's why it's called, it's close to 0. So that's why it's called the Zeroth Law. So it states the following, that if I have 3 objects, let's call them A, B, and C. All right, so these 3 objects are in equilibrium, okay? And if A is in equilibrium with C, and C is in equilibrium with B, then A is also in equilibrium with B. Now what does it mean? It means something very, very simple. It means something practical. I mean, it sounds like a mathematical theorem, but it's not. It's something very, very easy to understand. Suppose that I give you 2 cups of water, right? So this is cup A, cup B, and C is a thermometer, okay? So, well, I don't know how to draw it like this. So this is your C, is a thermometer. Now this principle tells you that if you want to see whether A is in equilibrium with B, you can do 2 things. One thing you can do is you put A in contact with B and you see if something happens or not. If they are not in equilibrium, then some heat is going to be transferred between the 2 cups of water. If you take one out of the microwave and the other is at room temperature, they are not in equilibrium, and you see that there is some heat transfer. Eventually they will equilibrate at the same temperature. Okay? Or there is another thing that you can do. You can take the thermometer, C, measure, put it in contact with A, put it in contact with B. If the thermometer is in equilibrium with A and with B, which means they have the same temperature, you know that if you put them in contact, nothing will happen. Okay? So it's something trivial, straightforward, obvious. But it's something obvious that if you think about it, it's exactly what allows you, I mean, this principle is exactly what allows you to define a temperature scale. What is a temperature? Temperature is essentially, that's something that 2 systems have to have in common in order to be in equilibrium. Okay? That is temperature. So, and if you try to formulate in practical terms what it means to have in common something, well, then you invent a thermometer. For example, you take a system that has some property that depends on how hot or cold is the system itself. For example, if you take mercury, is the volume essentially. So it has a large coefficient, a large compressibility. I mean, the volume changes a lot with temperature. You can use any other thermometer. I cannot think about anything else at the moment, but I'm sure that. And then, taking this, why? No. So, and then if you take this principle, then you realize that if I want to know what is the temperature of a system, then the temperature is essentially that's something that A and B have in common on a scale of your thermometer in order to be in equilibrium with each other. You cannot define an absolute temperature using this Zeroth principle. You can just think, realize that the temperature is that function these 2 objects have in common, and that's it. Okay, so far for the Zeroth principle. Now the first principle of thermodynamics is, so the Zeroth principle is in a sense a definition of equilibrium, what it means to be in equilibrium. The first law of thermodynamics is instead a law that establishes that different forms of energy are exactly one and the same thing. Now, this is obvious to us. We know that heat and work are 2 different aspects of the same thing, which is just the energy of the system, right? Back at the beginning of when Napoleon was alive, roughly speaking, people didn't know this. People thought that heat is something that is transferred from one body to another body by some invisible fluid. Now in physics, you have all these invisible fluids, like it was called the heat fluid, the calorimetric theory of heat transfer. caloric theory, not calorimetric, caloric theory of heat transfer. There was this invisible fluid that was being transferred physically from one body to the other when you were, putting them in contact. There was another theory that was a molecular theory of heat that was related to the fact that it's what we accept now, that heat is nothing but a form of thermal agitation of molecules. The more heat you have in a system, the more your molecules move fast. Okay? And it's not surprising that at the beginning of the 19th century, everybody believed in the fluid and nobody believed in the molecules. The contrary of what happens now. But people slowly realized that through experiments that this caloric theory was not correct, could not be true. For example, one way they realized it was that if you try to drill a hole in a piece of metal. In those days, they used gun barrels, canoons, and they tried to drill a hole in a gun barrel. Then what happens is that you can continue this process indefinitely and heat up your system, your drill, as much as you want. And it's not that at some point this caloric fluid finishes and you cannot transfer anything else. As you continue drilling, the drill heats up, and there is no transfer from the barrel to your drill. But the real experiment that made people understand that actually work and heat are just two faces of the same coin was the experiment of Joule in 1840, in which what he did was the following. Joule, 1840. What he did was the following. He took a system, let's say a fluid, and he demonstrated by doing measurements that you can heat it up by performing just work on it. Okay? One way you could do that at home is you take a cup of water and you start stirring. You have to do it really fast. Okay, it's not that easy. But he did it by mechanical work, so by essentially friction. For example, between solids is much easier. You know pretty well that when it's winter, there's an efficient way to heat up your hands, which is to do this, right? And the temperature on the surface increases. That's exactly the demonstration of the Joule experiment. It's actually surprising that people did not realize this. So another way you can perform work on a system is by using electricity, right? You put a wire, for example, if we would put a tungsten wire in a well, you have actually a system that works like that, probably in your office or at home. One of those heat boilers, right? A boiler works like that. It uses electrical work to heat up water. And the work is just the integral of the current times the voltage difference. Okay? So anyway, he measured, he performed a certain amount of work on a system and measured the increasing temperature, and he demonstrated that by performing the same amount of work that he could measure, he obtained the same increasing temperature, right? And then that was enough to demonstrate that work and heat are just two faces of the same coin, two forms of energy. Good. Now, this said, then you can think about the following situation. Imagine that instead of having a generic system, we have a system that is thermally isolated. Okay? And we perform this Joule experiment on a system that is thermally isolated. Thermally isolated. There is no exchange of heat with the external environment. Then if we do this, what happens is that if you go from a state A to a state B along different paths or in different ways, okay, then you will obtain the same result, okay? So you will obtain, for example, take a thermally isolated system and perform the Joule experiment on this system. So you heat it up from a temperature T1 to a temperature T2 by performing work in two different ways. One way you stir it, one way you put the water in a boiler and you measure how much electrical work you're performing on the system. So these are the two things. And if Joule is right, and he was right, then what you will obtain in this thermally isolated system is that the amount of work you're performing to go from state A to state B is independent on the way you heat up your system, okay? So in other words, what Joule would say is that, the work is independent on the path, and in a sense, what we are doing when you're performing work on the system, on this thermally isolated system, you're just increasing its energy. So this is equivalent to the difference in energy between the final state and the initial state. That's how you define it. Okay? Good. Now, the point is that if you relax this constraint that we put on this experiment of being thermally isolated, and you consider a system that can exchange heat with the environment, okay, then you immediately realize that that work cannot be independent. The work that you perform to go from a state A to a state B cannot be independent on the path anymore. And let me demonstrate this easily. You can take a cup of water and heat it up from T1 to T2 in two ways. One way is performing some electrical work on it or stirring it very rapidly for a certain amount of time. The second way is you don't do anything on it, you just put it close to a hotter reservoir and you wait for the temperature to raise. And you see that in that situation, in one case I have the work that is equal to zero, in the other case I have a finite work. So it cannot be true that the work in this case of an open system does not depend on the path that you take, but depends only on the final and on the initial state. Okay? What is independent on the path that you take is actually turns out to be the difference between the work that is, let's say, done by the system and the heat that is absorbed by the system, or the other way around, depending on your definition. And this is exactly the first principle of thermodynamics. If I take the difference between the heat that is absorbed by the system and the work that is performed by the system, absorbed by, let me write it because and done by the system, okay, then this difference turns out to be what is known as a state function, the difference in values of a state function, internal energy, or in other words, turns out to be independent on the path that I take in parameter space. Okay? In other words, let's go back to the case of the cup of water. If I increase the temperature of the water by stirring vigorously, okay, I will perform a certain amount of work, delta W. If I increase if I do this by putting this in contact with a reservoir, heat reservoir, I will absorb a certain heat, delta Q, and it turns out that these two processes, delta W is equal to delta Q, okay? So if I define in the case number one this one. This is 2. Case number 1, I define my internal energy, delta U, as delta W. And in case number 2, I define my delta U in case delta Q. If the final state temperature and the initial temperature are the same, in two cases, these two delta U are going to be the same. Okay? And this is true for any process that connects T1 and T2. Okay? So you can choose of doing this in many possible ways, but in any case, you will always reach the same. If you count the difference between the work that is done by the system and or minus the work that is done on the system and the heat that is exchanged, that is released by the system, you will always get the same number. That is measured in Joule, essentially because Joule is the guy who understood all of this. Okay? All right. So, the reason I'm writing, so I have to specify one thing. So typically, well, if you read 2 books on statistical mechanics or entropy, you will see 3 different conventions, because people use the work done by the system or on the system, the heat released by the system or the heat absorbed by the system, and this will give you minus signs that will fluctuate around in the first principle, and you will never understand which one is. I mean, you have to think, okay? Every time you read a different book, you have to think, otherwise you get the signs wrong. So in my case, I will use the conventions absorbed by the system, done by the system, okay, for heat and work, which are the same conventions of Wang, of the book of Wang. Now, I will also write things in infinitesimal form in this way. This is done also in other books by, for example, by Atkins, which is another famous book on thermodynamics. So when you see this d bar, it means that this is not an exact differential. Not an exact differential means that, in a sense, dq, if I integrate this, dq is not independent on the path that I take to go from A to B. Okay? So what is an exact differential is the difference between dq and dw. Okay? So this is the quantity du, the difference in internal energies, that is an exact differential in the sense that if I integrate it, defines a state function that depends only on the value of the points I'm selecting, given a reference point. Great. Now, what is now the work? What it means to do work on the system? Well, it turns out, and this is a subtlety, it turns out that sometimes you have to think carefully when you solve exercises in thermodynamics, or when you try to use thermodynamics for real systems, about what is work and what is heat, because it's not so easy to distinguish the two. Let me make an example. If I take a wire, a metal wire, and I put it in water, and I start passing an electrical current, and I'm not inside, otherwise I'm dead. So what is going to happen is that due to dissipation, the water will heat up. Due to dissipation in the wire, due to the resistance of the wire, the water will heat up. Now, I can think about myself being outside of the water and having all this stuff in a container, right? In a black box. Now, the only thing I see is that I'm operating this machine with some electrical current from outside, and I have a voltage difference, so I can measure the work that is done on the system, which is just the voltage difference by the current, and I know that this produces a heating up of my fluid. Okay? So in that case, you just say, okay, look, I have this is clearly a case in which I'm doing an electrical work on a system to produce a heating up of of the fluid. But if you look at it from inside, what you have is just a wire that is extremely hot because of the resistance, and that is exchanging heat with the environment, okay? So in this case, there is a bit of ambiguity depending on how you think about your system, about what is heat and what is work. But if you stick to your conventions, the only thing I can promise is that when you use properly the first principle, everything will work out, because in any case, you're taking these differences between work and heat, and provided you don't count twice, things will be properly accounted for, okay? Now, to do work on a system, you can do many, many things. For example, your dW could be equal to, okay, so I thought it was too late. Your dW could be equal to PdV. Now, what is PdV? PdV is the simplest type of work you can perform. You know that if I take a ball and I want to push it, right, with a force, F, and I push it by dx, then the work that I'm doing on the system is dW equal to F times dx, right? A basic definition of mechanics. Now, if I have a piston now, and here I have a fluid, some gas or something, and I push this piston with a force to cover a certain dx, then of course the dW is going to be equal to F times dx, but this can be written as F divided by A times dx times A, and F divided by A is the pressure I'm exerting on the piston, while dx times A is nothing but the difference in volume of my container. So that's the logic behind this writing, okay? So this is mechanical work. Then I can have also, for example, if I have a spin system or a magnetic system, I could perform work by, for example, applying a magnetic field. Because if I have a certain magnetization, right, and I apply a magnetic field, what is going to happen is that all my magnetization will tend to rotate in the direction of the magnetic field, or actually in the direction, yes, in the direction of the magnetic field. And then what I'm going to have is a dW which is equal to minus h times, which is a vector, times dm, which is also a vector in general. Okay? And this is going to be my magnetic work. You can experiment on this if you have a magnet and a strong enough magnetic field. Then you can, so this is magnetic. You have something analogous to this when you have a system that can be polarized electrically, okay? For example, the surface of a pile sweater when it's, that you will use when it's winter, at least in Trieste, that can be easily polarized by doing this. You know that? No. You know what is a pile? Is this
just a special fabric?
No. Use just wool, plain wool. Everybody knows what is wool, right? Okay, so that can be also polarized very easily. You can just rub on it, and how do you prove that it's polarized? Because you take a balloon once you inflate for kids, and you stick it here, and you will go around and walk around Trieste with a balloon sticking on your lamp wool. So anyway, if you have a system that can be electrically polarized, then you can do work on it by applying an electric field. And then in that case, the place of the magnetization will be taken by the polarization vector. And finally, so electric. Finally, you can do work, for example, against surface tension, right? For example, when you have a bubble and you want to inflate it, so to increase the area, the reason you have to push and suffer sometimes, I mean, depending on what is the surface tension, is that you are doing work against the surface tension. And this work against the surface tension is done by the pressure, essentially, in your system. So you could have something like that, minus sigma times dA, where this is a vector normal to the surface you're trying to modify. Okay?
Sorry, the minus sign is because we define dW as work done by the system.
By the system,
okay.
Yes. And finally, so the minus sign is because I'm doing work on the system.
Yeah.
I'm thinking about it as work done on the system.
Okay.
Well, it's all a mess of science, okay? So let's take that properly. And then you can also have chemical work, which is defined in this way, which is what happens when I have a certain substance and I try to increase the number of molecules in that substance. It turns out that the work I'm doing on the system is proportional to something called the chemical potential, mu1. Okay? We'll see this chemical potential appearing everywhere, in particular the ground canonical ensemble. So this is chemical. So there are zillions of ways to perform work on a system. I'm sure you can think about many others. Now, all right. Now, the first law of thermodynamics then defines a state function, which is the internal energy. Unfortunately, I used the notations that are different to the ones I used in my notes. It doesn't really matter. The internal energy is a state function, and therefore U of xa, xb minus U of xa is equal to the integral between xa and xb, where xa and xb are some points in the in parameter space dx of d of the du. Now, if I have among all possible transformations, some peculiar ones are called cyclical transformations, because for cyclical transformations, the initial and the final state are the same, okay? And therefore, what I have is that the total change in internal energy is zero, which means that the work done by the system is equal to the heat absorbed by the system, okay? So for cyclical transformations, what I have is that integral over the cycle of dE is equal to 0, which implies that integral over the cycle dW is equal to the integral over the cycle of dQ. So in other words, the total work done on the system by the system is equal to the total heat absorbed by the system. Okay? Now, the next thing we have to do now is to express essentially the differential of internal energy, or the heat absorbed by the system, in terms of variations of state parameters. Now, I will always have in mind, one can have in mind many things, but let's stick to one example. So we will have in mind from now on gases. Gases in which the state of the system can be described in terms of the usual variables: pressure, volume, temperature, and number of particles. And we know that these four variables are not all independent. There are only three of them that are independent and can be varied. If you vary, for example, in a gas pressure, temperature, and number of particles, the volume has to change as well in order to be in equilibrium, right? So let us now decide, for example, that we vary only temperature, volume, and number of particles. Then we know that d is an exact differential, so we can write it as d e dt at constant volume and number of particles, dt plus dE dV constant temperature and number of particles, dV plus dE dN constant volume and temperature dN. Okay? Now, given this expression, what is going to be dq? Now, the reason I'm deriving all these expressions for dq, etc., is not because I want you to suffer, is that the next thing I will explain is what are the specific heats. And what is the specific heat? Specific heat is essentially defined by the amount of heat that I need in order to raise the temperature by a delta T. So in order to figure out what is the specific heat in various situations in which I fix the volume, the pressure, or whatever, I need to write down what is dq in all these situations. Okay? So that's why I'm writing these expressions. So if I fix the pressure and I vary temperature, volume, and number of particles, then dq is going to be equal then to d plus dw. dw is pdV, okay? And therefore I'm going to have d dt. We understand that constant volume and whatever, so I'm not going to rewrite these subscripts all the time, otherwise we'll stay here until tonight. So dt plus d dv plus p dv plus d dn dn. Okay? So this is the first situation. Here I'm fixing pressure and changing these three variables. Now what happens now if I fix the volume and I change the pressure? Well, in this case, what I have is that my dV is going to be dV dt at constant pressure and number of particles, dt plus dV dP at constant temperature and number of particles, dP plus dV dN at constant pressure and temperature, dN. And therefore, using the analogous expression for dE, so dE is going to have something analogous to this. I'm not going to write it. Something similar. Then what I'm going to have is that dq is equal to I forgot one thing in the previous one. Sorry, guys. Yeah, sorry. If I change the number of particles, I'm not only performing work pdV, but I'm performing work P dV minus mu dN. Okay, so I forgot a chemical potential here. Minus mu dN. Look at the previous expression. Okay? So here I will have something similar. I will have dE plus P dV minus mu dN. And then I use the expressions for dV that I just found, and I will have d dt plus P dV dt dt plus d dP plus P dV dP dP plus dE dN plus P dV dN minus mu dN. Okay. And finally, well, I'll let you write it down as an exercise. We don't really need it. What happens when you fix the temperature and you vary pressure, volume, and number of particles. In this case, you will get that your dQ is equal to dE dP at constant volume and number of particles, dP plus dE dV at constant pressure and number of particles plus P dV plus dE dN minus mu, where this is taken at constant pressure and volume. Now, I don't know about you, but when I was a student like you and I was seeing all this dV, dP, dE, constant, this and that, I was getting infinitely bored. So if you are infinitely bored, I understand you. Okay? Let us now try to, after all this infinite boredom of 15 minutes, let us try now to derive some physics. So let us discuss the specific heats. So, as I just said, what is the specific heat? The heat capacity. The heat capacity is defined as C equal to dQ over dt. So, I mean, it's just the constant of proportionality between the heat and the difference in temperatures. Okay? So, if you want to know what is the heat that you have to give to your water in order to increase the temperature from, I don't know, from 30 to 100 degrees, you have to know this number, which can be dependent on temperature, but let's neglect all these details. All right, so now you can measure the specific heat in various circumstances. For example, you could measure the specific heat at constant volume or at constant pressure, right? Typically you say, okay, so what? What does it mean? Well, it means something practical. When you do the experiment of making pasta, in order to know how much gas you're paying, you need to know what is the specific heat at constant pressure, because the pressure is constant and the container is open and the pressure is constant, is 1 atmosphere. If you're making coffee, right, in the mocha, in order to know how much money you're spending to making your coffee, you need to know the specific heat at constant volume. So you see, it's important to know what is the specific heat at constant volume and at constant pressure, because it's about money. All right? Good. So now that we understand this, let us now find out what are the expressions for the specific heat at constant volume. Now, in order to figure out what is the specific heat at constant volume, we just go back to the situation in which the volume was constant and we were changing only pressure, etc., etc. So, which is this one, right? So, in this case, the specific heat at constant volume, we find it to be equal to the derivative of the entropy with, I'm hungry, sorry. The derivative of the internal energy with respect to the temperature itself, okay? So we get CV equal to dE dt at constant volume. If you go back to the previous expressions again and you want to find what is Cp, well, you just go to the next line, you go to the one that is proportional to dt, and you read it out, and it's d dt at constant pressure here, plus p dv dt at constant pressure. So this is going to be your expression, dE dt at constant pressure, plus p dv dt at constant pressure. All right, so now, what is the expression now of the difference between the specific heat at constant volume and at constant pressure in the simple case of an ideal gas? Well, it turns out that you can find it out easily, because for the ideal gas, we know that P for the ideal gas we know that P times V is equal to N times R times T. Okay? And therefore, we know that dV dt at constant pressure is equal to N times R divided by P. Correct? And therefore we know that P dV dt at constant pressure is equal to N times R, which implies that CP is equal to dE dt at constant pressure plus N times R, while CV is equal to dE dt at constant volume. Okay? Now, in principle, these two equations do not allow us to say anything about the difference, because here we have derivatives, one at constant pressure, the other one at constant volume. In principle, they might be different. However, it turns out, and this is again an experimental fact, that internal energy of an ideal gas depends only on the temperature itself and on nothing else. Okay? I repeat it. The internal energy of an ideal gas depends only on the temperature, does not depend on pressure, does not depend on volume, depends only on temperature. If you think about it, it's obvious. It's just kinetic energy, because it's a non-interacting gas of particles. So it's just particles that move around, do not interact between each other, are just moving each one independently. The only energy it has is the kinetic energy, and the kinetic energy is determined by the average velocity. But the average velocity is just determined by temperature. Think about, I'm sure that all of you know what is the Maxwell distribution. So it's just determined by temperature. So only temperature determines the internal energy of a gas. Okay? And therefore, since only temperature is intervening, what we have is that these two derivatives are the same, which implies that Cp minus Cv for the ideal gas are equal to N is equal to N times R. Okay? And in particular, if I consider the specific heat, which is the heat per mole, so I divide by little n, then I will have little Cp minus little Cv equal to R for the ideal gas. Okay? So you see that this gas constants has actually a very precise physical meaning. That's the difference between the two specific heats. All right, now as an application now, let us consider as an application of what we just said, let us consider the adiabatic transformations in an ideal gas. So with the n equal to 0, so we don't consider changes in the number of particles. So adiabatic transformations are all transformations that occur in a system that is thermally isolated. So there is no exchange of heat with the external environment. Okay? Now, in this case, you can write down dq as Cv dt plus pdv, right? If you're varying, for example, temperature and volume, right? That is essentially this first formula that I wrote down here. Sorry, where is it? Oh yeah, it's this one. And it's simply related to the fact that internal energy does not, for an ideal gas, does not depend on the volume, right? So I'm specifying this one to this case. All right, so now this one has to be equal to 0. Okay? Now, therefore, I can rewrite this as well, first of all, I can notice that P times V is equal to N times R times T, and therefore I can rewrite my pressure as N times R times T divided by V. Therefore, the previous equation can be rewritten as N little Cv dt plus nRT dV over V equal to 0. Okay? And therefore, what I have is that dt over T is equal to minus R over Cv dV over V. Okay? Which implies that if I integrate it, means that the log of T final minus T initial is equal to minus R over CV times the log of V final over V initial. Okay? Which implies that T final over T initial is equal to V initial over V final to the power R over CV. Or in other words, T initial times V initial to the power gamma, I will define gamma in a second, is equal to T final V final to the power gamma, where gamma is equal to R divided by little CV, which is nothing but, since R is Cp minus Cv, right? We discovered it before for the ideal gas. This is nothing but Cp over Cv minus 1. And of course, this is not gamma, but it's gamma minus 1. I made a mistake. So this is gamma minus 1. Is it correct? No. Here I have to put a minus 1. Okay, now it's correct. All right? Now, suppose that I want now to, so this is the equation that has to be, if I have a process at constant, an adiabatic process in which I vary temperature and volume, this is the relation between the final temperatures and volumes and initial temperature and volumes that have to be satisfied in order for the system to be adiabatic. Okay, so this is the constraint, this one. Now what happens if now I change variables and I go to, let's say, pressure and volume? Well, it's straightforward because we can still use the equation of state and write, for example, the temperature in terms of pressure and volume themselves. Temperature is P times P divided by M times R. Right? And therefore, what I will have is that using this equation, let's call it alpha, using alpha, I will have P times V, P initial, V initial, V initial to the power gamma minus 1 equal to P final, V final, V final to the power gamma minus 1. And therefore, if I put everything together, I will have P initial, V initial to the power gamma equal to P final, V final to the power gamma. So this is the second version of the constraint for adiabatic transformations. And finally, the last version is what happens if I consider temperature and pressure. If I consider temperature and pressure, I can easily, again, change variables. I can write my volume as N times R times T divided by P. Do the same calculations as before. Use alpha or beta or whatever you want, and you will obtain T to the power gamma, P to the power 1 minus gamma, equal to T final to the power gamma, P final to the power 1 minus gamma. And that is it. Okay? So these are the relations for adiabatic transformations that you find. Now my suggestion is learn these relations if you didn't, and if you don't know them yet. Learn them very well because they will be very useful for all possible exercises. Okay? I'm sure that all of you have practiced a lot adiabatic, isothermal, etc., transformations, but they are typically very useful for exercises. So next time, I don't want to start now because it doesn't make any sense. Next time we're going to start discussing the second principle of thermodynamics, and then we are going to have fun with all possible cycles. So I'm going to do the Carnot cycle, then what is the Carnot cycle, the Stirling cycle, the Otto cycle, the Diesel cycle, the, what else? The Diesel cycle, the Joule-Brighton cycle, and that's it. So, at the end you will know all the cycles. And I'm going to explain how a car engine works, which is the most important thing, right? You want to know what is the efficiency, the thermodynamic efficiency of a Ferrari, right? Good.